All right, welcome back to CFD. Today, Dr. Saad's out of town, so I'll be giving that lecture. It's mostly hands-on coding for the 2D Poisson equation, as we'll see now. So this is the slide where we left off last week. Did we forget something? So last week we did, if you remember, unsteady advection and unsteady diffusion in 2D. But if you look at the Navier-Stokes equation, it's not just advection and diffusion. We still have the pressure term that we need to take care of. And it might not be obvious from the equations in themselves, but we don't have an equation for the pressure. So as we will see on Thursday or next week, we'll end up solving this equation for the pressure. Nabla squared of P is equal to some right-hand side source terms. And Nabla squared, as you know, is the Laplacian, the second derivative. And in 2D, Nabla squared is del squared P over del x squared, the second derivative in the x direction, and del squared P over del y squared, the y derivative in the y direction. And the source term can be a function of space and time, and/or time. So it's s of xy. So if we use a second order central scheme, same way we did for previous equations, like the heat transfer problem, the del squared P over del x squared can be approximated as pi minus 1j minus 2 pij plus pi plus 1j for the x direction. And for the y direction, it's pij minus 1 minus 2 pij plus pij plus 1. And over delta x squared, delta y squared. And the source term is just the source term at point ij. So on a 2D grid, it would look like this. This is the point you're solving the equation on. It's node ij. And these are the four other neighboring points in the x direction and the y direction. And if we rearrange this equation to show a coefficient multiplying each term, we'll get this equation, exact same one, just rearranged. And note that the coefficient for Pij is the sum of the other coefficients. This will be an important note for later on when we'll be deriving the Navier-Stokes finite volume equations. And now we want to solve that one. This is the Poisson equation for the pressure or temperature if you're looking at steady state heat transfer. All right, and when we go into finite volumes, it will be more convenient to use this notation. So the cell you're solving the equations at will be referenced as C for center or cell. And the neighboring points will be east, west, north, and south. It's more convenient to name them using these names instead of I and I minus 1 and j plus 1. So this would be the new equation at point C at this point. So now we want to solve that equation. And to do that, remember from the 1D steady state heat conduction in rod, what we did was we assembled the matrix to solve Ax equal to B, and then we inverted A to get X equal to A inverse times B, if you remember. And we used np.linear solve to invert that matrix. In 2D, it's the same thing. To get your matrix, you need these terms, the coefficients for every point, and then assemble your matrix and then invert it. But in 2D, it's much more complex than 1D. And at a later stage, we will assemble that matrix. But for today, we're going to use a different approach to solve that equation. This is what we're going to cover now. So there are different methods to solve that system of equations and representing the coefficient matrix. But the easiest methods are iterative solvers. If you remember from your undergrad numerical methods, probably taken iterative solvers. And what iterative solvers do is they take that equation that we just derived, and they solve it at every point ij, instead of inverting the whole matrix in one shot. And to do that, we write the equation at point ij, because we're going to solve p or t or any scalar at node ij. And the right-hand side would be all the other variables. So we're just rearranging that equation. We've not introduced any other notation or another term. Just taking the Pij to the left-hand side and everything else to the right-hand side. All right, so how do we solve it? The simplest method is the Jacobi iterative solver. You've probably seen that in undergrad numerical methods. So what we do is we take an initial value for P, pressure or the temperature or the scalar field, at iteration 0. K is the iteration number. And then from these initial fields, we can compute an UP at point ij. That's why we're calling it Pij superscript k plus 1. It's the pressure at the next iteration, which can be computed by this equation for the pressure, but using values of the previous iteration, as opposed to what we've done in the natural solve, where we one shot just by inverting that matrix. But inverting the matrix is expensive, especially for large systems. That's why it's much faster to do that iteration, going over every point, ij in your domain, and then using your previous values to get your k plus 1 estimation. And then when you get pk plus 1, you insert it back to here, and you get k plus 2, and then k plus 3. And you keep iterating until your p k plus 1 doesn't change much from pk, the previous iteration. Now, if you notice, if I'm looping over points ij, then I've already computed pi minus 1j just before that point, and pij minus 1. Because if you're looping over points, you'll be doing for I from 0 to your endpoint, and from j equal to 0 to your endpoint. Then you've probably calculated these already. So an improvement to the Jacobi iterative solver is the Gauss-Seidel, which says that always use the most recent information you have when possible. Because we have already computed these values, we can just evaluate them at iteration k plus 1. And that should improve conversions, yes?
So the k plus 1 is that's the pressure value in the next time step?
Not time step. This is steady state. Next iteration. So you take initial guess for your pressure, you guess it. Let's say it's all zeros. And then you loop over your nodes and compute this guy, Pij.
Oh, okay.
You'll get, so if these were P0, your initial guess, you'll get P1 at point ij. You do that for all values of I and all values of j. So you cover your whole domain.
Okay. And so each iteration gets you closer and closer to that.
Exactly, yeah, to your steady state solution. When you get P1 ij at every point, you plug P1 here, you get P2 ij. And you keep doing that until your pressure doesn't change from your past iteration. So Gauss-Seidel, use your most recent information to get improved conversions. A third method is successive over relaxation, which it's a slight modification to that equation by introducing this number beta here. And this change of equation is supposed to give better conversions. We'll do the three methods, and we'll show that this is an improvement to this one, and this is potential improvement to this one. These are some of the iterative solvers available. Again, these were covered in undergrad numerical methods. These are links to Professor Saad's lectures, where he explains iterative solvers. You can take a look at them. And we will also review iterative solvers in detail later in the course. So for now, we just need the three equations I've showed you. All right, so let's take an example. We'll code this one now. So this is a 2D plate. It's a square. And the boundary conditions are p equal to 1 on this side of the left wall, and p equal to 0 elsewhere on the boundary. And in the interior points, the source term is 0. There is no source term pressure equation. Don't think of it as pressure. It could be temperature. P is just a variable name. But we're using P to get used to pressure as a variable, because we'll be mainly using this equation for the pressure in Navier-Stokes. So get your Jupyter notebooks. Right, I'm gonna make it light color. Can you see? All right, so put some title here. So we want to solve the following equation. Nabla squared of b is equal to some right-hand side. Just pasting stuff I already have. You don't have to write everything for now. I'm just pasting the equation to use as a guide while coding. Right, so this is Pij without the iteration number. This is the governing equation that we're solving. Pij is equal to some source term multiplied by some coefficient plus the other 4 neighboring points also multiplied by some other coefficients. So first we import our boilerplate modules. All right. First, we define the domain. So Lx, let's give it 1.0. Ly, also 1.0. Doesn't have to be a square, but we'll start now by setting Lx and Ly equal to 0. Then number of nodes in each direction, Nx, let's say 51 for now. And Ny also 51. So essentially dx and dy would be equal in that case. And they also don't have to be. So x, the x coordinate would be np.linspace from 0 to Lx, and then the number of points in x, which is nx. And y, the location in the y direction is np.linspace 0 Ly and y. Now x and y are just 1D arrays. We want to convert these into a full grid with dimensions nx times ny, and at each node we get the x position and the y position. And to do that, as we did last time, xx, yy equal to np.meshGrid with arguments x and y. np, that one. All right. So now we need to make sure that xx and yy are correct. We can just type plt.imshow. Show, and the argument is xx. All right. This is the x position. It's constant in a vertical line. And then yy would be the opposite, starting from 0 up to 1. All right. So now we need our initial guess for the pressure. We can just initialize it as zeros. Yeah.
Your question, I just noticed this now, but why is it on the y-axis it goes from 50 to 0 instead of 0, 0?
Yeah, that's a Python indexing issue. It's not an issue. It's it shows you the way a Python indexes stuff. It will get you the last entry at the bottom. And that wouldn't be an issue because later we will be indexing ji for variables. So that fixes that issue. All right, so we initialize our pressure to some initial value. Let's initialize it to 0. So MP dot zeros. And P is a 2D variable, so it needs, it has dimensions of nx times ny. Again, for that issue you just raised, we index y then x for that exact issue. And that's why the argument for the np.0 is a list starting with ny, comma, nx. Now, in that example, nx is equal to ny, so it doesn't make a difference. But in general, we always start with y and then x. This is the initial guess for the pressure. Right. S, the source term on the right-hand side, is also 0 in that example. In the next example, we're going to take an actual value for S, but for now, it's just ny and x, full of zeros.
So this is just trivial?
Sorry?
The source term is just like, we're going to change it next time.
Correct. We don't have to program it in this example because nabla squared of p is equal to s equal to 0. Yeah. But in the next example, we're going to have some source term in the middle of the domain. So we're going to need an s variable. All right. So now we're ready to iterate. So to do that iteration, we're going to need a while loop. And the condition to enter that while loop, to iterate again, to take another iteration, would be that our error is still above some threshold, some tolerance, right? And while that error is still above what we want to iterate. So this is our condition, which means we now need to define some tolerance. Let's say 10 to the minus 5, some small number. And then we're going to have to initialize our error. Otherwise, you'll get a syntax error in Python. And this error should be initialized to a large number, at least larger than the tolerance we specified. You can just 10 to the power 10. It doesn't matter, just a large number. So that you ensure that when this while loop is evaluated, you're going to enter it at least once, because the error is already greater than the specified tolerance. And then side.
If we didn't specify error, then error is basically 0?
Not really. It's not a variable. So when Python will evaluate that, it will tell you error is not defined to throw a syntax error. Right. It will tell you name error is not defined. So we define it before the while loop. All right. So first, we grab our previous iteration, the value of p from the previous iteration. So pk, we're going to name it k, p underscore k, is p dot copy. And we can, I can explain to you why we do the dot copy function here instead of doing just p underscore k equal to p. You never want to use that statement.
What statement?
pk is equal to p. That's going to be a problem later. We can go over it after that session if you want. So just add the dot copy function after it. So this grabs your previous p value that you've updated from the previous iteration. In this case here, it's going to be the p0, the initial guess, and then assign it to pk. Right? Then we define some boundary conditions. So what are the boundary conditions in that case? Go back to the example. P is 0 everywhere on the boundary, except for this small strip here. So we define it by starting with the, let's say, the top wall. And what's the index of the top wall?
0.
It has to be a 2D index, so it's
All comma 0.
the top wall would be -1 in j, because remember we index in j first and then I.
Yeah.
So j equal to -1 is the last entry, the highest point in your y axis. And then for x, it's all x values, because your whole top wall is at 0, equal to 0.0. Let's comment that as top wall. Bottom wall, what's the j index? 0, comma, semicolon, correct.
Semicolon?
This, not semicolon, colon, yep. And this would be your bottom wall. For the right wall, what's j in that case? All j's, right? And at which x value, at which I? -1, correct. Equal to 0, 0, because p is 0 at that location. We specified that value, and this would be your right wall. Right. Now for your left wall, we have two conditions, right? P is equal to 0 in this bottom and top part, and p is equal to 1 on this middle part. So it's easier to first set everything to 0 and then override this part to 1, instead of having to set 3 different sections. So p at all j's and I equal to 0 is 0. And this is your left wall. And then some part of p is at 1. Some part of the left wall is at 1. So which j values you choose? There's no specific height here. So let's say it's a third. So we know that we have 50 elements. We defined nx to be 51, ny to be 51. So we have 50 spacings here, 50 small segments. Or let's say it's 10 here, 10 that has p equal to 0, 10 that have p equal to 0 here, and then 30 that have p equal to 1. So we start with 0.10 and then to -10.
Can you also go 40 first?
Sorry?
Would be going to 40 the same?
Correct, yep.
Yeah.
But I'm doing it symmetrically so that if I change 51, let's say 101, then we would be doing from 0.10 to 90. That would be correct, yep. And you could also create functions or compute them mathematically. I'm just typing 10. I want the 10th node to start at p equal to 1. But if you want an exact number, then you have to write some code here to get that index. OK, so j from 10 to -10, and then I is still 0 because we're at the left wall. And this would be equal to 1. This is also for the left wall. These are the boundary conditions. Comment here. Boundary conditions. Boundary conditions. So here, let's say, grab previous iteration. P. OK, so you grab your previous iteration P, then you assign your boundary conditions, and now you can update the value of P at Pij. Now to do that, we're going to loop over all values of I and all values of j, and to do that by using a for loop. So for I in, and then we use this function range. We could start from 0, but 0 is specified by the boundary condition. So we don't need to override that one. We can start from the interior point at I equal to 1. And then we end at nx. But nx is also a specified value because there's a boundary condition on the right wall. So we can stop at nx minus 1. The nx and 0 points are taken care here in these boundary conditions. That's why we stop at an x minus 1 and we start with 0.1.
Oh, so you're doing your central difference scheme.
Only on the interior point. Yeah, because the boundary points are taken care of in the boundary conditions. We don't need to update them. So here we loop over I, and then we need to loop over j. For j in range. So 1 to ny minus 1. All right, so when we loop over these points, we're going to want to apply that equation. We're at point ij, and we want to compute this right-hand side here. Let's program it. So P at ji, remember we index with j first. So P at that node we're currently at is dx squared, so dx. If you notice here, there's a common factor, 1 over 2 delta x squared plus delta y squared. So let's program that first. 1 over 2 over dx squared, so dx times dx, plus dy squared, so dy times dy. And this factor multiplies dx squared dy squared Sij, so dx times dy times dy, times the source term, so s, at point j comma I. In this case, all s values are 0, so it won't matter. But again, we're going to cover an example that has non-zero values for s, so we're going to include it now. Plus the second term, which is the x derivative here, second derivative. We've already accounted for this term, 1 over 2 delta x squared plus delta y squared, so we need to add delta y squared times this here. So dy times dy times. Now we need to grab the p-values from the previous time step, from the previous iteration, sorry. And these values are saved in the pk, not in the p, because we want the old iteration values. So it's going to be pk. And for the index, it's I plus 1, j, so we're going to write here j, I plus 1. And then pk, j, I minus 1.
Should we not also multiply that by 1/2?
I took the 1/2 outside here. It's multiplying everything.
Oh, I didn't see that bracket.
Yeah. Instead of having to retype 1 over 2 every single time, because it's common to the 3 terms here. And then the last term is dx squared, dx times pk at j plus 1I plus pk j minus 1I. That should be it.
Sorry, could you make that a
Yeah, sure. Right, so we forgot to do one thing. We did not define the x and dy yet. That's why it's highlighted here. So we can do that after we define x and y. The x is just x1 minus x0. And dy is y1 minus y0. This is j minus 1. So here in the range function, it should be a comma, not a colon, because these are arguments to the range function.
So does that divide sign at the beginning, 1.5?
Here,
Yeah, so the divide sign right after
2.
2, that means dividing the whole segment there?
Yeah, so 1 over 2 over, it means it's 1 over 2, and then 1 over 2 over this guy here.
Okay.
This is equivalent to that term, 1 over 2 delta x squared plus delta y squared.
Yeah, but you said you took it out from all terms.
Correct, yeah, that's why it's multiplying this term, this whole term.
Oh, that one bit.
Yeah, that whole term is multiplied by this one.
Oh, I see what you did.
Instead of having to type this for every term, just do it once. Okay, so we've updated our P field. We have pk plus 1, and we have pk from the previous iteration. Now what we do is we update the error. We want to make sure, we want to check if P has converged or not. So we create a new variable called diff, stands for difference. And then the difference would be the new P minus the old one. So P minus pk. Now P is a 2D array and pk is a 2D array. So difference would be a 2D array whose elements are the difference between these two. But the condition here is just a number. It's an error. And how do we summarize a matrix into a single number? What did we do in the homework? Sorry? Oh, no, we do an error norm. We take a norm, like the L2 norm, or the L1 norm, or the L infinity. So to do that, let's update the error here. And we're going to use linalg and p.linalg.norm. The argument is the diff matrix, the diff array we defined, and 2 for L2 norm. If you put 1 here, it's going to give you the L1 norm, and if you put inf here, it's going to give you the infinity norm, L infinity. We're interested, we're good with the L2 norm here. So you update P, you compute the error or the difference between P at the previous iteration versus current value of P, and then if that error is still above your tolerance, you iterate again. You get a new P. And then you do that again until your error is below a certain tolerance that you have defined here. Now, the problem with this while loop here is that if your system is not converging, it's going to be an infinite loop. If your error does not get below 10 to the minus 5, your code won't stop running. So to do that, to prevent that, we're going to set a limit. Not only the error should be still above the tolerance, but we're going to add an and here. And the current number of iteration is still lower than the maximum allowed iteration. We're going to call these variables it for the number of iterations, and the max it, which is the maximum number of allowed iteration. Which means we need to define here what is the maximum number of iterations, let's say 100. So even if I do 100 iterations and my error is still high, I'm going to stop looping, whatever the error is. And we need to define that it variable. We're going to initialize it to 0. And then after every single iteration, I'm going to increment it by 1 to indicate that I added one more iteration. I've performed one more iteration here. So there are two conditions to exit that loop. If your error is below your tolerance, then you have converged. No need to do any more iterations. Or you have exceeded your maximum allowed number of iterations, which is set here to 100.
Could you have it print out your total,
Sure, yeah. I was going to get to that now. So if you run this and it converges or doesn't, you won't get any indication. It won't tell you which condition was satisfied. So what we're going to do, we're going to add an if statement here. If it, so the number of performed iteration, is equal to the maximum number of iterations, then we have not converged yet because we have done that maximum number. We're going to print to the user solution did not converge in, and then the number of iterations. So this will tell the user solution did not converge in IT, the variable we defined. So we did 100 iteration and the solution did not converge. And it's also helpful to show the error committed. So we did 100 iterations. We did not converge, and the error for that was error equal, and then your error variable here. If IT is not equal to the maximum number of iteration, then your solution has converged. So we're going to print here else print solution has converged, and then we're going to tell the user how many iterations it took. So n, and then the number of iterations, and the iteration string here. We good? Take your time. I'm going to name that one the Jacobi iterative solver, because we're only using the previous iteration values for the p-values here. What's the error?
Type range is not subscribable.
Used square brackets here for range. It's a function, so parentheses.
Thanks.
There's no dt. dt is for time. It's steady state. Where do you have dt?
I get an error says built-in function or method object is not subscribable.
Which one? Which line? It will tell you.
In P and S, when I define P
Yeah.
as np0.zeros.
Oh, here?
Oh, that's why. I didn't.
Yeah, so np.0 takes a list if you want to do 2D or 3D. And the list items would be ny, comma, nx, comma, nz, and so on.
So the solution did not converge in 100
Yep.
iterations.
So we did 100 iteration, the maximum allowed number, and it did not converge, and it reported the error, which is greater than the specified tolerance. We wanted the error to reduce to 10 to the minus 5. It did only reduce to 0.034. So if I increase the maximum number of iteration, here, 200, it's going to do 200. It's going to decrease the error, but still much higher than the tolerance. If I increase the tolerance, let's say 10 to the minus 2, let's do 500 maximum iterations. Solution has converged in 361 iterations. So we know here that the error is this much. All right, so now we want to plot our solution. Remember, it's a 2D plot, so we're going to use plt.contourf to fill the contours. And the arguments for that function would be xx, yy, and then the p-value. plt.contourf. Now, it's bad practice to plot stuff in your loop here, because whenever you run that cell, it's going to compute everything again. But for this problem, it's very fast. Takes 2 seconds, so it doesn't really matter. But later in your codes, you should probably compute your solution and then start plotting in a new cell, so that when you execute that plot, it's not going to run this while loop again. Right? I'm going to keep it in one cell for convenience now. So this is the solution. Let's add the color bar to see the values. plt.colorbar. 0 to 1.05. This is probably, the solution has not converged yet. The error is 10 to the minus 2, 0.01. That's why you see values that are higher than 1. We're going to reduce that error in a bit. But this is your boundary condition where p is equal to 1. And then this this temperature, if you want, or scalar is diffusing until 0 here on this boundary. Now we can increase the number of levels here. We were only saying 1, 2, 3, 4, 5, 8 levels or 7. So we do that by adding an argument in the contour f, levels equal, let's say 100. Then it's going to give you a smoother plot for your variable here. Also, let's use a different color map, not the default one. So CMap is jet is usually a good one when you're doing heat transfer because it shows high values as red. Think of it as a hot condition, and blue as the cold one. Also, Inferno is a good color map for this example. See this one. Okay, I'll add a label for x and y, plt.x label.
My
X.
solution is converging in 1 and 2 iterations.
Did you plot it? It's not going to be that.
Yeah, no, it's not working.
Yeah, let's see.
So mine is less than 0.99 or less than 1.
Yeah, it depends on your solver. 0.99. When I run it again, it changed because this tolerance is very high. But as you've noticed in the Jacobi solver, 500 iterations is not enough. It's not converging in 500 iterations. When I'm going to do Gauss-Seidel and the successive over-relaxation, it's going to converge in much less number of iterations. It's okay. We can let it. We don't have to converge it for now. What was your problem?
It's converging in 1 and 2 iterations.
Are you incrementing this inside the while loop?
Yeah.
Try starting your kernel and then starting again. And are you setting pk equal to p dot copy? And it's not working yet. Can check it for you. Why is printing 2 times? It should print 1 time. It's executing 2 times. It's very weird. Oh, you're here. This is a post-processing after your for loop.
Okay.
It doesn't explain why it's stopping. Have that inside your while loop, it will print at every iteration. But now, we have the exact same code.
Should I just copy it into new?
Try that, yeah. But we have the same code. I mean,
Yeah.
did you double check that one, if it's correct? Dx squared plus dy squared. Yeah, that's it. Oh, yeah, you still have an issue on that equation here. So it should be 1 over 2. Okay, correct. Yeah, that's it here. This, and then closes here. Then you need 2 parentheses here. Yeah, that's it. Sure. So 100 iterations is not enough, as you've seen. Increase it to 500. It's not gonna converge still with this tolerance, but that's fine. Okay, that was the Jacobi iterative solver. Let's try the Gauss-Seidel. So if that equation worked for you, just copy and paste it here. And the only thing we need to change is we're not taking p-values at iteration k anymore. We're taking the most recent available values, which is just p. So for I plus 1 and j plus 1, p is equal to pk, because we've not gotten to these points yet. But pi minus 1 and j minus 1 have already been updated in these 4 loops. So by setting everything to p instead of pk, you're going to get the Gauss-Seidel solver. Run it again. All right, so solution still is not converge in 500 iteration, but the error is much lower. So what we'll do is we're going to reduce the tolerance to 10 to the minus 2, just to illustrate the difference between these 2 solvers. Going to run Jacobi first. It converged in 361 iterations, so I'm going to save here. Mark down. So Jacobi took 361 iterations. Let's see Gauss-Seidel. 308 iterations for the exact same error value. So same solution, exact same solution for much less, which is, let's say Gauss-Seidel. 308 iterations, much faster. Did you get it working? Nice. Okay, the third iterative solver we're gonna try here now is the SOR, successive over relaxation. And it's the exact same equation as this one, so I'll copy and paste it here. Let's go back to the slides. We have a constant beta multiplying these 3 terms here, and then plus 1 minus beta pk, the pressure at the previous iteration, ij. So I'm going to include these here. Instead of 1 over 2 over this common factor, this one will be multiplied by beta. And then we add to these 3 terms here, plus 1 minus beta times p, pk, at ji. All right? This is the SOR equation. Now we need a value for beta. In the slides here, you see beta is between 1 and 2. If beta is equal to 1, then this term cancels out. It's going to be 0. And then beta equal to 1, you're going to get your Gauss-Seidel solver. And then the maximum of 2 here is for stability. So we're going to try values of 2 and higher, and you'll see that the solution will diverge. The only stable solutions are between 1 and 2. So let's try it. let's choose beta is equal to 1. For beta equal to 1, we should expect the same convergence criterion here, still 308. Which is not surprising because when beta is 1, this term cancels out, and this one is 1 here. Let's say beta is 1.5. Solution is converging in 184 iterations. Exact same solution with roughly half the number of iterations. So SOR, beta 1.5, 108 iterations. Let's increase it. 1.75, conversion in 102 iterations. So you're getting faster and faster convergence when this number increases. Five, 102. 9.5, let's increase it even more. And you're gonna start getting higher number of iterations. So the ideal value would be closer to 1.75 or 1.8. 1.8 is even better.
What normally determines the value of beta? Is it just
I think it's trial and error. You can't just get it, because for different problems, if you change your boundary conditions, you're going to get different values.
But at some point, you start getting diminishing returns because your value, the change in your error becomes less and less. So, like you went from an error of 1, which is 208 or 308, whatever.
The number of iterations, yeah.
Yeah, the number of iterations, and then you would jump to 1.5, it became 1.
But this is not error. This is a beta. This is a factor.
Yeah.
It doesn't change your error. It changes your number of.
Sorry, your number of iterations.
Yeah.
Yeah. So you're.
It's diminishing return, but if you find that optimal value, you won't do any more. So I see what you mean. So you're saying that by trying to find beta, you're not going to get much better convergence.
Right.
Yep. So you can stick with 1.75.
Yeah, like trying to
Correct,
find,
yep.
like find 1.85 or 1.9.
Exactly, yep, you're right. Now, if beta is 2, that's not going to converge. We've got some weird stuff. So remember when we did stability conditions for the integrators, and you got the maximum CFL number and the Fourier number. This is a similar study that can be done here to find your maximum beta. And if beta is less than 1, then it's probably going to diverge too, or converge. So when beta is less than 1, it's called under relaxation. Under relaxation, it's higher stability, but lower convergence rate. That's why you're requiring much more iterations compared to Gauss-Seidel. But we're not really interested in under relaxation here. Let's keep it at 1.75. So now, because of good convergence, I can reduce my tolerance. Let's go to 1 to the minus 5. It converged in 339 iterations, while the Jacobi iterative solver would probably need, like I tried it before, like 10K iterations just to converge that system. While using SOR with the beta 1.75, you've converged with only 339 iterations. All right? Questions?
So your tolerance on your previous solution.
Yep.
How tight do you really want that to be? I mean,
It depends on what you're trying to do. If this is a pressure value and your pressure is in pascals and it's 100K, like your average, then you don't really need that tight tolerance. But if your scalar goes from 0 to 1, maybe, then you probably want a much smaller tolerance. Because the 0.01 tolerance would be 1% of your solution. While if your variable is much larger, has larger number, then 1 to the minus 2 would already be a very small number. So it depends on your application. So before going to the next case, here we're covering constant boundary condition, or Dirichlet boundary condition, we call them. And what's interesting about this code here is if I want to add the source here, like I want to set p equal to 1 on this segment, I can just do that by going to the bottom wall and saying from for all j's, from x is 30 to 40, I'm going to set p equal to 1. And if I do just that, go to the bottom wall, and then say p at 0j, and for I values ranging from, let's say, 30 to 40, I'm going to set this equal to 1. You're going to get that source term here. And you can add whatever values you want along these 4 walls. That's what's nice about this method. You can go to your top wall and then add a condition here. Say the whole wall is at p equal to 1. So the Dirichlet boundary conditions are very simple to do. What else do you want to show? Yeah, there's a neat trick in Python too. If you want to hide these white lines, your contour lines, you can add this command. So I'm going to save my contour into a variable called CNT, then add this line. And this will essentially remove your white contour lines here. It will set the color of these edges to the face color, which is the actual contour color here, which is nice. Questions on that problem? All right. So on the second one, exact same boundary conditions, but you have a source term in this middle section here. So remember, your source term is defined here. We have initialized it as zeros everywhere. If I want to add source term, I just write S for j's ranging from, let's say, 20 to minus 20. And let's make it a square. So both in x and y, in I and j, it's going to be 20 to minus 20 and 20 to minus 20. And this value, let's set it to 25. And then run it. You're going to see some source term here. It's not as strong, so let's increase that to 50. Right. So we have this boundary condition at p equal to 1, and then we have this source term. Could be a heat generation. Like, let's say 50 watts of power are generated in this region here, which also diffuses to the outer boundary. And S is a constant, doesn't change. That's why we're not updating any value of S here. It's a user-specified value. You can add the second source term, so let's shift this one down to here. So in J, it's going to be, instead of 20 to minus 20, let's say 10 to 20. You're going to shift your source down. And then you can add another source at 30 to 40. You can add as many sources as you want in your domain. Simple enough? All right.
So is this just for t equals 0?
No, that's steady state at t equal infinity.
That's steady state.
Yep, correct. If you want to do it unsteady, we're going to have to do the unsteady diffusion we did previously. And what's nice about unsteady diffusion is that it's explicit. The values at n plus 1 depend only on the values at n. So you don't have this implicit equation for p. So if I go back to this one here, we don't have that problem. Pij is not anymore a function of only its neighboring points. Because if you want to solve this one exactly, you're going to need these values. And these values depend on their neighboring points. And you're going to get this whole connected system, which we call an elliptic equation. And that's why you need to solve the whole matrix in one shot, the system of linear equations. If this was unsteady diffusion, then you would have some time derivative here. And then you discretize it as Pn plus 1 minus Pn, where n is time. the index in time, over delta t. And then you evaluate p of n plus 1 at the right-hand side that only contains p-values at n, which you already have from previous time step. So you will be doing what you're doing in unsteady advection and diffusion. If you want to get just the steady state solution, then you have to pay that price to solve everything as an implicit system of equations. And you avoid solving that whole matrix by using iterative solvers while you do several iterations and then try to converge your initial guess for p into a steady state one, which should be converged to your tolerance, which we specify here, within a maximum number of iterations specified here. Now, the final case we're going to look at is with what we call Newman boundary conditions. And while p equal to 1 is the Dirichlet boundary conditions, where your variable is set to a value, the Newman boundary conditions is when the derivative of that variable is equal to some right-hand side here. So how we deal with Newman boundary conditions? This is a grid, arbitrary grid. And at these boundary points, we know that del p over del n, where n is the normal vector, the direction, is equal to alpha. Now we know that these interior points obey the previous equation, this one. Pij at these interior points obey the Poisson equation. But points here do not. They obey this equation. Del p over del n is equal to alpha. And we can model del p over del n by using finite differences. The derivative of a variable is, for a right wall, for example, it's the value here minus the previous point over the spacing, the normal backward differencing for spatial derivatives. So the equation would result in p boundary, the value of p at this node, minus p interior, the value of this variable at this node, over h, the spacing delta x for this case, is equal to your specified flux alpha, your boundary condition. Now we're solving all these points in the interior using the equation we're using for Pij. After you do that, p at the boundary can be deduced from p interior, the values we've just computed, plus alpha, your specified flux at that boundary, times h, which is delta x in this case. For a top wall, it's going to be the same equation, but h is delta y. On a left wall, you're going to get a minus because the x direction is positive in that direction, from left to right. So your approximation for the derivative is interior minus boundary. This node minus that node. That's why you get a minus here if you arrange this equation. And h is delta x here, spacing in the x direction. For the bottom wall, it's going to be h is delta y. So the derivative here is interior minus boundary over delta y. You arrange it to get p boundary is interior minus alpha h. Let's code this. So these are not valid anymore. P at the top wall is not 0 anymore, nor at the bottom wall or the right wall. P left is still a Dirichlet boundary condition. We're specifying a value of 1. But for the other, we're going to have to use that equation, these 4 equations here. Let's start with the right wall. P at the boundary is interior plus alpha h. Right wall is here. So P at the boundary is the interior point, which is all j's at I minus 2. Right? So minus 2 is the node to the left of minus 1, the interior point right next to the boundary point. And this is going to be minus, no, it's plus, I think. Yeah, it's plus. Alpha times h, which is dx here. Now for the left wall, it's Dirichlet. Bottom wall, it's the interior one, so not 0, 1, j equal to 1, and then all i's, minus alpha times dy, because dy is the spacing for that derivative on the bottom wall. And then for the top wall, the interior point is p minus 2 at all I plus alpha times dy. Now we need to specify alpha, so let's put it here, alpha. Let's say 0. When the derivative is equal to a 0, that means it's an outflow boundary condition. The flux is 0 at that location. Let's keep S as it was, 20 to minus 20. All right, now if we run this, let's remove the source term for that one. All right. So note how these contour lines are exiting perpendicular to the boundary. All these contour lines, because the flux is 0. The derivative of pressure is 0 at those points. That's why the contour lines in white are perpendicular. I'm not sure if it's visible. Here.
So in the other scenario, our alpha would be infinity.
Or any positive or negative value. So let's put alpha as 0.2 or 0.5. You're going to notice that the contour line exit or enter the domain at an angle. And that angle would be the derivative of P. All right? When alpha is 0, then you're going to get perpendicular, 0 flux. And you can turn off or on that source term. Doesn't matter. So here, all the contour lines are perpendicular to the three surfaces. Also note that alpha doesn't have to be a constant. Here, I can have an alpha for the top wall, an alpha for the bottom wall, and an alpha for the right wall. They don't have to be equal, right? So this could be 0.1 times the x, this could be 0.2, and this could be 0.5. There's no reason the flux has to be equal. These are user specified. You can choose whatever value you want. Also, alpha doesn't have to be a constant, or even the Dirichlet boundary conditions. So if you go back to the previous example we had with the Dirichlet boundary conditions, let's do this. In this case, the left wall is at p equal to 1, and all other walls are at 0. Also note here that the contour lines do not cross the boundaries. This is because all the boundaries are at a specific value of p. You don't have a flux here.
So this other condition, this is saying that our pressure is not static at the boundaries.
Here it is.
Yeah, here it is. But
Yeah.
the other condition.
The derivative of pressure is static.
Okay, but there's flux going in and out of our.
Correct.
Okay.
Yeah. Correct. That's why you could see values larger than 1. To satisfy this condition, you might need to increase your temperature or pressure or whatever variable you're solving for in these interior points. So you're going to update the interior points to satisfy a constant or a given flux, specified flux at the boundaries. Now, what I wanted to show you here in that example, where the left wall is at 1 and the right wall is at 0, this Dirichlet boundary condition of 1 doesn't have to be a constant. I can set it as any profile I want. Let's try sine function. So instead of having constant value of p, I can just write np dot sine and then y. And then you can notice here the value of, let's use different frequency, 2 pi times y. np dot pi. So when y is around 1 here, your sign would evaluate to -1. And then near 0, it will evaluate to 1 here in this bottom region. So you have different values for p, and they're user specified. They don't have to be a constant along that boundary. And these do not have also to be zeros. You can set the right wall to be a cosine. You can do whatever you want with the boundary conditions. Their values, they're fixed in time because this is steady state, but they don't have to be set in space, constant in space. And this is for the third example. Also for Newman boundary conditions, alpha doesn't have to be a constant. Alpha could be a sine function. You want a sinusoidal flux on that region, on that boundary. And so alpha would be np dot sine of some function of x and or y. Questions? All right, so this is it for today's session. I'm going to stay here for a couple of minutes if you have questions on the homework. Also, I'm having office hours from 6 to 7. Feel free to join too if you want.
For tomorrow?
Today.
Okay, today.
Yeah.
Is that here?
I know it's on Zoom. The same help session link for the Zoom. Try to join around 6:30 because I'm meeting 2 students from 6 to 6:30. So if you want, join after that. Sure? Any question about today's material, the coding?
Yeah, I'm going to review it tomorrow and go through it again.
All right,
If I have
great.
any questions, I'll ask them.
The homework's due tomorrow, I think midnight.
I think I got that already in today.
Great.
Yeah, your advice for that last problem is very helpful. Thank you.
Sure.